Hi, hello everyone.
Good afternoon.
Good afternoon, nice to see you. So, last time we introduced Carnot's cycle and derived equation which defines the performance of Carnot cycle. We have shown that efficiency of Carnot cycle is defined only by temperature of the hot and cold reservoir and does not depend on the working substance and design of the engine, which works according to Carnot cycle. So that's ideal cycle. It's so-called reversible cycle. And means that it has the highest possible performance for any heat engine. A little bit earlier, we also introduced the second law of thermodynamics in terms of the concept of heat engine, which claims, like, defines the working conditions for heat engines or heat pumps. So it depends in which mode they operate. The formulation is a bit different, but it defines the like kind of direction of thermodynamic processes. And today we are going to start our discussion of a new state parameter, which is entropy. And introduce this concept of second law of thermodynamics in terms of this new state parameter entropy. To be more specific, change of entropy, which brings some physical meaning with it. So today we will discuss entropy from the macroscopical point of view. Later, we will also consider microscopical features of this concept. So let me change to the slides. Why does that work? Okay. Now it works. So, as I said, entropy is a new state parameter we will consider, and we'll consider it first from macroscopic scale, as it was first introduced in something like 1865. So initially, entropy was considered just as some useful concept in thermodynamics. However, over time, with the establishment of statistical mechanics, which describe behavior of a system with many particles, it became like revealed its fundamental importance as a state parameter. To be more specific, let us consider some closed volume, which is divided in two chambers with some wall. So one is filled with gas, another is empty. So if we get rid of this wall inside the volume, the gas will be evenly distributed all over the volume of the container. And that will correspond to the macro state with the highest number of possible like microstates, which describe position of each of these particles, like atom of the gas. So that is steady state condition with so-called highest statistical weight. Means that this macro state can be described with the largest number of microstate parameters. It is possibility, but very, very small possibility, which is approaching to zero, that over time, all molecules of this gas will come back to the left half of this container, even without the wall in between. However, this is negligibly small probability. The highest probability of steady state condition is the even distribution of molecules all over the volume, means when there is the highest number of possible microstates to describe the system. And all systems, like isolated systems, they tend to reach this state with highest disorder. And because highest disorder means the highest number of possible microstates to describe the system. So if we introduce this term disorder, which every system would like to reach over time on its way to thermal equilibrium condition, we can claim that entropy as a new parameter is some way of a measure of this disorder. In other words, we can say that in every isolated system, change of this entropy is denoted with capital S, is always positive or equal to zero. So if we know that system, isolated system, over time always tends to go to some equilibrium condition with the highest level of disorder, means that entropy, and if we consider entropy as the measure of this disorder, entropy should increase or remain constant, means change in entropy should be positive or equal to zero. So in particular, if we have some reversible cycle like Carnot cycle, then change of entropy over this cycle will be equal to zero. However, all real systems which are defined by irreversible processes will cause eventually increase of entropy. So if we, how can we define quantitatively this parameter entropy. So actually, change in entropy means the differential of the state parameter entropy provides some physical meaning and can be defined. So in general, if we consider some small change of a system, which is at equilibrium condition, and during this small change, some amount of energy in form of heat, delta QR, means a small change of heat provided during reversible process is transferred to the system. And then the change of entropy, which is now the differential of entropy, can be defined as, so it's equal to the amount of energy transferred in this reversible process in form of heat to the system, divided by temperature of the system. So that is dQr divided by T. So here we need to specify that temperature is considered to be constant, because this change of the system is very small. Change of the equilibrium thermodynamic condition is very small. If it's very small, then we can, with good level of in first approximation, assume that temperature remains constant. So that is the definition of change of entropy. And it is necessary to highlight that entropy is a state parameter, and its change during some process depends only on the final and initial states. So it doesn't depend on the path of this process. And that is important factor which we will mention a little bit later. But so far we just need to highlight that this is state parameter, and its change is defined only by initial and final state. So if the change of thermodynamic condition of the system is not very small anymore, then larger change in entropy, so instead of differential ds, we can put delta s, already should be defined via an integral. So we need to integrate from initial to final state ds. And that should be integral from initial to final dQr over T. So we cannot assume temperature already a constant. So we need to integrate it and take into account also change of the temperature. What is important for reversible cycle, when we have like closed cycle, it's integral along a closed loop, dQr over T should be equal to 0. That's what I mentioned in terms of Carnot cycle, closed Carnot reversible cycle, a change of entropy is equal to 0. So if we define this for Carnot cycle, we can show the following. So change in entropy should be equal to QH absolute value divided by temperature of hot reservoir minus QC which is heat provided, like expelled to the cold reservoir, divided by its temperature. If we recall our previous discussion, we have shown that the ratio, the absolute value of the ratio QC to QH is equal to TC divided by TH. So taking this into account, we can easily show that specifically for Carnot cycle, only for Carnot cycle, this ratio is valid. Delta S will be equal to 0. Change of entropy for Carnot cycle will be equal to 0. Because this is so-called reversible cycle. And this statement that change of entropy in isolated system is always larger or equal to 0 is the definition, another form of formulation of second law of thermodynamics, because it shows us the direction of thermodynamic processes which are possible. Other conditions than increase or constant entropy, they cannot happen by itself. So you need to perform work, external work on the system, then the system is not closed anymore. And then you can only reduce entropy of the system, but that is because of intentional work provided to the system from outside. If the system is closed, all processes during the establishment of thermal equilibrium condition for this particular closed system will result in either constant or increased entropy. So that is actually also true for the such global system as universe. It continues to transfer toward highest probability macro state, and thus experience this increase in entropy. So if we consider the state of perfect disorder, which is equilibrium condition for the system, for universe, and that implies that there is no energy which could be available for performing some work, that automatically means that eventually, along this evolution of universe, all atoms and elementary particles in the universe will vanish. So it will just be very long process of decomposition of matter transformation to accumulating centers in black holes, which eventually also will vanish, remaining just empty space, which means that this increase of entropy defines the behavior of all thermodynamic systems, including universe. So that was the introduction of the concept of entropy, and we should definitely try to be able to calculate the change of entropy for different processes in ideal gas. So that will be another part of our discussion today. And ideal gas is a very good reference system for deriving these equations. So we will do this on the example of ideal gas, and we will start from isobaric process when, by the way, can you remind me, please, what is constant at isobaric process?
The work on the system is 0.
Oh, that is Isohoric process, that constant volume. Work is defined by change of volume.
Or internal energy is constant.
Oh, that is isothermal process because then temperature remains constant. Isobaric process, that's process with constant pressure. So please.
Oh, sorry, I misheard you.
No problems. Just good to recall this. So we have isothermal process with constant temperature, isohoric process with constant volume when work is equal to 0. We have isobaric process, which is stands for process with constant pressure, and adiabatic process when we don't have exchange of energy in form of heat. So these are 4 most important processes which can happen in ideal gas. So let us try to calculate and derive equations for the change of entropy. In the case of ideal gas, first we start from isobaric process. Pressure is equal to constant. So we know that differential of entropy is defined as dq over just temperature. So how can we represent this change in heat? So 1 over T times, we remember from first law of thermodynamics that it can be actually defined as change in internal energy plus some work done by the system, with P pressure remains constant. So how can we represent each of these parameters? So that will be equal to 1 over T. Change in internal energy can be represented via the specific molar heat capacitance, C at constant volume, CV times nu, number of moles, times delta T, change in temperature. And also, we would like to express pressure in another form. So what can we do for that purpose? We can recall the equation for the state of ideal gas, which is P times V equals to nu times RT. So based on this, we can express that P is equal to nu times RT divided by V. So let us substitute this instead of P here, and we will have nu times RT divided by V times dV. So now let us open the parentheses. We will get the following. So it will be CV times nu times dt over T, and it will be nu times R. Temperature will be cancelled out. Nu times R times dV over V. So here we have two terms. which define the change of entropy. One responsible for change in temperature, another for change in volume. So if we want to determine some large change of entropy, when we have two states, initial and final, quite far away from each other in terms of thermodynamic processes, then we go as follows. That is integral from initial to final state over this differential ds, and that will be integral of these two terms which we got, responsible for change in entropy because of change of temperature and because of change of volume. So in these cases, we will have CV times nu integral from T1 to T2, which stands for temperature at the initial and final states, dt over T, then plus mu times R integral from V1 to V2. It also stands for volume at initial and final states, dV over V. If you recall this table of integrals, dx over x integral is natural logarithm of x, and that's why these integrals will be equal to CV times nu, these are constants, times natural logarithm of T2 divided by T1. And also we have another term which is responsible for the change of volume, mu times R, the universal gas constant, natural logarithm of V2 divided by V1. So we got these two equations. What we can do now, first of all, maybe let us rewrite it on the next slide so we have more space, and then we will have it in front of us so we can proceed further. Delta S is equal to CV times nu times natural logarithm of T2 divided by T1 plus nu times R, natural logarithm of V2 divided by V1. We recall from previous discussions that CV is equal to 2/3, like 3/2 of times R, universal gas constant. And also we need to mention that for isobaric process, the ratio volume to temperature is equal to constant. So we actually can write that V1 divided by T1 should be equal to V2 divided by T2. Or from here, we can write that V2 divided by V1 should be equal to T2 divided by T1. So you see that we have two natural logarithms here with T2 divided by T1 and V2 divided by V1. And based on this ratio for isobaric process, which we consider right now, we have shown that V2 divided by V1 is actually equal to T2 divided by T1. So we can substitute this second natural logarithm with the first one, and that will be valid. Also, we can substitute instead of CV, its expression, 3/2 times R. So now let us do these substitutions. Delta S is equal to 3/2 times R, let's write times nu R, natural logarithm T2 over T1. Here we also write nu times R, natural logarithm, and instead of V2 divided by V1, we can write T2 divided by T1. T2 divided by T1. So now we actually can take out of parentheses nu times R times natural logarithm T2 divided by T1. And here we will have 3/2 plus 1. Eventually we get 5/2 nu R natural logarithm T2 divided by T1. So this is the expression for the change of entropy in isobaric process. Obviously, we can also write that 5/2 nu R natural logarithm V2 divided by V1. So that is also valid equation for calculating the change of entropy, because we can deal with change of volume or change of temperature. Since both are changing, because during isobaric process, we have a change of internal energy. We have heat, like energy transfer through the interface of the system in form of heat, and also some work done because volume is not remaining constant. So that is what we need to know about change of entropy during isobaric process. However, there are other processes and we need to consider them also. So let us consider next adiabatic process. We remember that the dq is equal to 0. So there is no energy transfer by heat in the form of heat during adiabatic process. If that is true, then ds is equal to dq divided by t, and that is equal to 0. So change in entropy during adiabatic process is equal to 0. So isothermal process. So for isothermal process, temperature remains constant. Means that if we again write here this equation which we derived for change of entropy, let us write it here. So we have it. Delta S has two components. It has component first, which will be CV times nu integral from T1 to T2 dt over T plus Another component responsible for change in volume, nu times r, integral from V1 to V2, dV over V. So in this case, for isothermal process, T1 is equal to T2, and means that we do not have this contribution from the term responsible for the change of temperature. Means that this integral T1 to T2 dt over T will be equal to 0. So in this case, only second term matters, and change in entropy during isothermal process can be represented by nu times r times natural logarithm of V2 divided by V1. It can also be written in another form, sometimes convenient, nu times r times natural logarithm of V1 plus delta V divided by V1, and eventually we get nu times r natural logarithm of unity plus delta V divided by V1. So means can write here initial. So we can calculate it via change of volume divided by initial volume of the ideal gas during isothermal process. Also, we have one more process, which is Isohoric process. And in this case, maybe let's try to squeeze it here. So we can still see this equation. During isohoric process, volume remains constant. So it means the second term does not have impact on the change of entropy, because this integral will be equal to 0. So change in entropy will be defined as CV times nu times natural logarithm of T2 divided by T1. And in other form, it can be represented similar to the previous one, will be CV times nu times natural logarithm of unity plus delta T divided by T initial. So these are the equations for calculating the change of entropy during 4 most important processes in ideal gas. So we considered isobaric, adiabatic, isothermal, and isohoric process. So summing up our today's discussion, so we introduced the concept of entropy, define it as state parameter which for isolated system increases or remains constant, and that actually defines the direction of thermodynamic processes, which can happen by themselves in isolated system without external effect on this system. So that is the definition of second law of thermodynamics in terms of this new state parameter entropy. We derive equations for calculating change of entropy of an ideal gas during 4 most important parameters: isobaric, isothermal, adiabatic, and isohoric processes. So if you have any questions, you're welcome.
Sorry, on the last slide, in the top right corner, the equation is, it's like for all processes we started from, right?
Yeah, we actually it is, because the thing is why we started from isobaric process, because as I mentioned, during isobaric process, we have changes in all three
parameters. Oh, okay,
yeah,
so now it makes sense.
Yeah, so we have change in internal energy, energy transferred in form of heat, and work done. And then if we derive equation for that particular scenario, then it's easy to exclude those components which do not make contribution, and step by step consider all other processes.
Okay, now it's clear. Thank you.
You're welcome. Yeah, so we will continue our discussion of entropy from the point of view of micro states during our next discussion on Wednesday. So hope you will join, and hope to see you next time, and wish you good.
Sorry, one more question.
Yeah. Sure.
In the course syllabus, there is no date for the end term. Are we gonna have like an end term this week, or when do we have it?
What do you mean under?
I mean, there should be like an exam or something.
Oh yeah, sure. We have final exam.
Yes.
Yeah, which will be it should be at the early next week, I think.
Okay.
Yeah.
I just couldn't find it in the syllabus. Sorry.
Yeah. It was not known at that time because it's scheduled later. But it's going to be early next week. We will send you like email with notification when it happens. So it will be similar to other midterms. We are long kappa, and it will just include problems from all cores.
Okay, thank you.
Sure, no problems. Okay, have a good day, and see you next time. Bye-bye.
Thank you.
Very much. Bye.
Bye-bye.